Hello there, and welcome back to the Sleepy Ocean. Tonight, we are setting our course for the absolute bottom of the world, navigating through the freezing, churning waters of the Southern Ocean to find a creature that was, for a very long time, nothing more than a whisper in the logbooks of sailors and a scar on the skin of whales. We are descending into the midnight realm of the colossal squid. To understand this animal, we must first understand the isolation of its home. The Southern Ocean is a ring of water that circles Antarctica, unbroken by any landmass, allowing the winds to whip up the fiercest storms on the planet. But beneath these violent waves lies a world of crushing stillness and sub-zero temperatures. It is here, in the mesopelagic and bathypelagic zones, often deeper than 3,000 feet, that the colossal squid drifts. The water here is so cold, it would freeze human blood in seconds, yet it does not freeze the ocean because of the immense pressure and salinity. This is a place of perpetual darkness, a cold, heavy void where the only light comes from the creatures themselves, and silence is the rule of law. The creature that rules this frozen kingdom, scientifically named Mesonicoteuthis hamiltoni, is a biological marvel that redefines our concept of size. While the giant squid is famous for its length, the colossal squid is built for mass. It is a tank compared to the giant squid's torpedo. If you were to see one suspended in the water, you would be struck by its width and its weight. It is estimated to weigh over 1,000 pounds, perhaps reaching up to 1,500 in the largest females. This makes it the heaviest invertebrate on Earth. Its body is shorter and stouter than its giant cousin, a compact muscular cone designed not for long-distance marathon swimming, but for explosive power and immense durability against the crushing weight of the deep. It is a creature of substance, a massive, gelatinous presence that displaces the water with a heavy, silent authority. The scientific name, Mesonicoteuthis, translates roughly to middle claw squid, a reference to the terrifying weaponry it conceals within its arms. But the story of its discovery is one of fragments and mysteries. For decades, it was known only from 2 tentacles found in the stomach of a sperm whale in 1925. Scientists looked at these tentacles and realized they bore hooks unlike anything ever seen. It wasn't until the 21st century that whole specimens were finally caught, usually by accident on long lines set for toothfish. Before this, the colossal squid was a ghost. It existed only as a hypothesis constructed from beaks found in the guts of wandering albatrosses and the scars seen on the flanks of sperm whales. It is a reminder that on this planet, a creature the size of a minivan can hide from humanity for centuries simply by living a few thousand feet deeper than we can reach. The mantle of the colossal squid, the main body of the animal, is a masterpiece of deep-sea engineering. It can be nearly 10 feet long on its own, a thick, muscular cloak that houses the internal organs. Unlike the firm muscle of a surface squid, the flesh of the colossal squid feels soft, almost like semi-solid gelatin. This is not weakness, it is adaptation. At these depths, having a body filled with gas or hard bone would be fatal due to the pressure. By composed of tissues that are high in water content and chemically balanced to match the density of the surrounding ocean, the squid becomes incompressible. It does not fight the pressure, it becomes one with it. This gelatinous consistency also makes it neutrally buoyant, allowing it to hang motionless in the water column without expending a single calorie of energy, a silent drifter waiting in the dark. Attached to this massive mantle are 2 enormous fins, shaped like diamonds or hearts, which provide the squid with its primary means of propulsion. In most squid, the fins are small and used for steering, while the jet propulsion does the work. But the colossal squid is different. Its fins are massive, spanning the entire width of the mantle. It uses them to swim with a slow, rhythmic undulation, rippling the margins of the fins to glide forward or backward with surprising grace. This mode of swimming is silent and energy efficient, perfect for a predator that relies on stealth. When it needs a burst of speed, it can still use its siphon to jet water, but for the most part, it hovers on these undulating wings, looking like a massive, dark spacecraft maneuvering silently in the void. The most famous feature of the colossal squid is undoubtedly its eye, which holds the title for the largest eye in the entire animal kingdom. It is the size of a soccer ball or a large dinner plate, measuring up to 11 inches in diameter. To put this in perspective, it is larger than the human head. This eye is not built for seeing color or fine detail. It is a light bucket. In the depths where the colossal squid lives, the only light is the faint blue downwelling sunlight from the surface or the bioluminescent flashes of other animals. The massive pupil of the squid's eye, which can be 3 inches across, gathers every possible photon of this scarce light. It is a biological telescope pointed into the darkness, designed to detect the faint, moving shadows of prey or the glowing approach of a predator long before they are close enough to be a threat. This colossal eye is equipped with a built-in searchlight. On the ventral surface of the eyeball, there is a specialized organ called a photophore. This organ produces its own light, a form of bioluminescence. The purpose of this eye shine is believed to be a form of counter-illumination or a searchlight to spot prey. By emitting a faint glow, the squid can erase its own shadow against the downwelling light, or it can use the light to illuminate the reflective eyes of fish or squid swimming nearby. It is a hunter that carries its own lantern, a secret beam of light that it can turn on and off, scanning the immediate darkness for the glint of a scale or the flash of a fin. The lens of this massive eye is a hard, golden sphere the size of an orange. Unlike a human lens, which changes shape to focus, the squid's lens moves back and forth like the lens of a camera or a telescope. When researchers examined the lenses of captured specimens, they found that they were incredibly clear, despite the animal being dead. In life, this lens would focus the image onto a retina packed with millions of photoreceptors. The visual processing power required to interpret the signals from such a massive eye is immense. A significant portion of the squid's brain, the optic lobes, is dedicated solely to vision. In the silent black world of the Antarctic deep, vision is life, and the colossal squid has evolved to see the unseeable. The orientation of the eyes gives us a clue to the squid's hunting strategy. They face forward and slightly upward. This suggests that the colossal squid is a sit-and-wait predator that hangs in the water column, looking up. It scans the water above it for the silhouette of a toothfish or a smaller squid swimming against the faint light of the surface. This sniper scope vision allows it to target prey that is oblivious to the danger lurking below. The squid uses the darkness of the deep as camouflage, hiding in the basement of the ocean while watching the activity on the floor above, waiting for the perfect moment to launch its attack. Extending from the head are 8 thick arms and 2 long tentacles, the tools of the squid's trade. But unlike the giant squid, whose arms are lined with suckers containing small serrated teeth rings, the colossal squid has evolved a weapon that is far more terrifying: swiveling hooks. The arms are short and incredibly broad, wider than a human thigh. Lined along the inner surface are 2 rows of hooks buried in the muscle. These hooks are made of chitin, the same material as a crab shell, and they are razor sharp. They can rotate 360 degrees. When the squid grabs a prey item, the hooks swivel to dig deeper into the flesh, ensuring that escape is physically impossible. The more the prey struggles, the deeper the hooks sink. It is a grappling system designed for a world where wet, slippery things are hard to hold. The two feeding tentacles are different from the arms. They are the long-range artillery. At the end of each tentacle is a club, a widened, muscular pad. On the colossal squid, this club is armed with the largest hooks of all, some measuring nearly 3 inches long. These hooks are curved like the talons of a raptor or the claws of a cat. The squid can shoot these tentacles forward with explosive speed, snagging a fish from yards away. Once the hooks on the club engage, the squid retracts the tentacles, pulling the victim into the embrace of the 8 arms, where the swiveling hooks take over to secure the meal. This combination of reaching hooks and holding hooks turns the squid into a shredding machine, capable of subduing prey that is large, powerful, and fighting for its life. Deep in the center of this ring of armed limbs lies the beak, a structure of black, hard chitin that looks remarkably like the beak of a giant parrot. This is the only hard part of the squid's body, aside from the hooks and the lens. The beak is surrounded by a massive ball of muscle called the buccal mass, which operates the jaws with incredible force. The colossal squid's beak is larger and more robust than that of the giant squid, designed for shearing through tough flesh and bone. It does not chew, it slices. The lower mandible overlaps the upper one, creating a scissor-like action that can effortlessly cut the spine of a large fish. It is a tool of dismantling, hidden in the center of the soft, gelatinous body, a black guillotine that delivers the final bite. Inside the beak is another tool of destruction called the radula. This is a tongue-like organ covered in rows of tiny, sharp teeth, functioning like a biological file or a conveyor belt. After the beak slices a chunk of meat, the radula grabs it and pulls it down into the throat. The radula also helps to grind the food into smaller pieces. This is crucial because, in a strange quirk of cephalopod anatomy, the squid's esophagus passes directly through the center of its donut-shaped brain. If the squid were to swallow a piece of food that was too large, it could suffer brain damage or cut off the blood supply to its brain. Therefore, the beak and radula must work together to process the meal into manageable bites before it is swallowed, a delicate culinary requirement for a monster of the deep. The metabolism of the colossal squid is a subject of intense scientific curiosity, and all evidence points to a lifestyle of extreme lethargy known as metabolic suppression. In the freezing waters of the Antarctic, chemical reactions happen slowly. The colossal squid lives life in slow motion. It is not a high-speed cruiser like the tuna or the swordfish. Instead, it is an ambush predator with a very low metabolic rate. It requires very little food to survive, perhaps only a few ounces of fish a day to maintain its massive bulk. This low-energy lifestyle allows it to grow to such an immense size in an environment where food can be scarce and patchy. It sits in the dark, burning its fuel at a glacial pace, a giant that grows by doing almost nothing but waiting. The mechanism that keeps this massive animal neutrally buoyant is a chemical solution that tastes terrible to humans: ammonium chloride. Unlike fish that use gas bladders, the colossal squid fills its tissues with this lighter-than-water chemical. Ammonia is a waste product of metabolism, but instead of excreting it, the squid stores it in specialized fluid-filled vacuoles within its muscle fibers. This solution is slightly less dense than seawater, providing lift. This is why the flesh of the colossal squid, and many deep-sea squids, tastes like ammonia and is inedible to humans. The squid is essentially a floating bag of cleaning fluid. This chemical buoyancy is permanent and requires no energy to maintain, unlike a gas bladder which must be pumped up or deflated as the animal changes depth. The blood that courses through the veins of the colossal squid is not red, but blue. This is because it uses a copper-based protein called hemocyanin to transport oxygen rather than the iron-based hemoglobin found in humans. Hemocyanin is more efficient at transporting oxygen in cold, low-oxygen environments. In the frigid Southern Ocean, this blue blood is a vital adaptation. However, hemocyanin is generally less efficient than hemoglobin at holding large amounts of oxygen, which reinforces the squid's need for a slow, low-energy lifestyle. If the squid were to exert itself too much for too long, its blue blood would not be able to deliver oxygen fast enough to its muscles, and it would suffocate. It is a creature built for bursts of violence, followed by long periods of recovery, driven by the copper currents in its veins. To circulate this blue blood through its massive body and across its gills, the colossal squid possesses 3 separate hearts. There is one main systemic heart that pumps blood to the body and the brain, and 2 smaller branchial hearts, one at the base of each gill. The branchial hearts are booster pumps. They push the oxygen-depleted blood through the gills to be reoxygenated. This decentralized system ensures that the blood pressure remains high enough to circulate through the massive mantle and out to the tips of the long tentacles. The hearts beat with a slow, powerful rhythm. If you were to place your hand on the mantle of a living colossal squid, you might feel the thumping of these 3 engines working in sequence, keeping the life flowing in the freezing deep. The respiration of the colossal squid involves a constant, rhythmic pumping of water. The mantle cavity, which houses the gills, acts as a lung. The squid expands its mantle to draw water in through the collar, washing it over the feathery gill filaments where oxygen is extracted. Then, it contracts the mantle to force the water out through the siphon. This flow of water serves a dual purpose: breathing and locomotion. Every breath is a tiny push forward. The gills themselves are massive and complex, folded to maximize surface area. In the oxygen-poor depths, the squid must be incredibly efficient at extracting every molecule of oxygen from the water. It breathes the ocean, filtering the life-giving gas from the eternal cold. Deep within the head of the squid, encased in cartilage, are 2 tiny organs called statocysts. These are the squid's balance sensors, equivalent to the human inner ear. Inside each statocyst is a small grain of calcium carbonate called a statolith. As the squid moves, gravity pulls on this grain, rolling it around inside the chamber lined with sensitive hairs. This tells the squid which way is up, down, left, or right in the pitch-black void where visual horizons do not exist. The statoliths grow in layers, like tree rings, adding a new layer every day. By counting these rings, scientists can determine the exact age of the squid. Amazingly, these rings reveal that despite their monstrous size, colossal squids are young. They likely live only for about 2 years, growing at a terrifyingly fast rate before reproducing and dying. The skin of the colossal squid is a vibrant reddish-pink color, a hue that serves as a cloak of invisibility in the deep sea. In the ocean, red light is the first wavelength to be absorbed by water. It does not penetrate into the deep. Therefore, a red object in deep water appears jet black. There is no red light to reflect off it. By being red, the colossal squid ensures that it appears as a dark, featureless shadow, blending perfectly with the black water around it. The skin is also covered in chromatophores, pigment cells that can expand and contract. While it is unknown if the colossal squid can change color as rapidly as shallow water squid, the presence of these cells suggests it may be able to flush darker or lighter to communicate or camouflage, a shifting skin of living pixels hiding a giant in the gloom. The primary source of sustenance for this massive invertebrate is the Antarctic toothfish, a creature that is, in its own right, a monster of the deep. Often marketed to humans as Chilean sea bass, the toothfish can grow to over 6 feet in length and weigh hundreds of pounds. It is a sleek, oily fish that patrols the seamounts and ridges of the Southern Ocean. For the colossal squid, the toothfish represents the perfect meal, a high-calorie packet of fat and protein. The hunt is a game of patience played in the pitch black. The squid hangs motionless, its massive eyes scanning the gloom for the faint bioluminescence or the silhouette of a passing fish. When a toothfish swims within range, the squid does not chase it down. Instead, it deploys its tentacles with a speed that defies the sluggish pace of its metabolism. The clubbed ends of the tentacles lash out, snagging the fish with the curved, swiveling hooks. The toothfish, despite its size and strength, is instantly immobilized by the piercing grip. The squid then draws the fish into the crushing embrace of its 8 arms, where the beak can begin the slow work of dismantling the catch. This relationship between predator and prey is so tight that scientists often find the remains of colossal squids, beaks and flesh, inside the stomachs of larger toothfish, suggesting a brutal rivalry where the eater can easily become the eaten depending on the size of the combatants. The scars left by these encounters, and by battles with even larger predators, tell a story of violence written on the skin of the ocean's giants. The psads. Sperm whale is the only animal known to regularly hunt adult colossal squids. When a whale dives into the abyss to feed, it is entering the squid's territory. The ensuing battle is not a quick snack, but a brawl. The squid fights for its life using every hook at its disposal. It wraps its arms around the whale's head, dragging the swiveling hooks through the sensitive skin of the whale's face and jaw. These hooks leave distinct parallel scratch marks that can be seen on almost every adult sperm whale in the Southern Ocean. Unlike the circular sucker scars left by the giant squid, the scars from a colossal squid are jagged tears and slashes. While the whale almost always wins due to its massive skeletal structure and sonar, it rarely swims away unscathed. The face of an old sperm whale is a roadmap of these struggles, a textured history of deep-sea warfare where the squid left its mark before being consumed. Scavenging the leftovers of these titanic battles is the Pacific sleeper shark, a lethargic, grey-skinned shark that inhabits the same freezing depths. These sharks are often found with chunks of colossal squid flesh in their stomachs. While it is unlikely that a slow-moving sleeper shark could catch a healthy adult squid, they are the vultures of the deep. When a squid dies after spawning, or is mortally wounded by a whale and left to drift, the sharks move in. They use a suction-feeding method to pull the gelatinous flesh into their mouths, their teeth slicing through the soft mantle. This recycling of biomass is crucial in the nutrient-poor deep sea. The massive body of a dead squid, weighing half a ton, is a bonanza that can sustain a community of scavengers for months. The sleeper shark, drifting silently in the cold, is the final resting place for many of these giants, a swimming tomb that metabolizes the remains of the squid in the slow, cold digestion of the abyss. The vertical range of the colossal squid takes it through the most extreme pressure gradients on the planet. While juveniles are often found in the upper 1,000 meters, adults descend into the bathypelagic zone, living at depths of 2,000 meters or more. At this depth, the pressure is roughly 200 atmospheres, equivalent to having a heavy car pressing down on every square inch of your body. For a human, or any animal with air-filled spaces, this would be instantly fatal. But the squid is fluid-filled. Its body is a continuous liquid medium that is indistinguishable in density from the water around it. This allows it to move vertically without the risk of decompression sickness. It can slide up and down the water column, following the prey or escaping predators, unaffected by the crushing weight that defines the lives of hard-bodied animals. It is a creature of the deep liquid, perfectly equalized with the crushing hug of the ocean. The temperature of the water in this habitat is a constant challenge to the chemistry of life. The Southern Ocean. Deep water hovers between -1.8 and +2 degrees Celsius. It is liquid only because of the salt content. In this supercooled environment, the fluids inside the squid's body must resist freezing. The ammonium chloride solution that provides buoyancy also acts as a form of antifreeze, lowering the freezing point of the squid's tissues. Furthermore, the enzymes that drive the squid's metabolism are adapted to function in the cold. Most enzymes slow down and stop working as the temperature drops, but the proteins of the colossal squid are flexible and active even at freezing point. This biochemical adaptation allows the squid to process food, repair tissue, and fire its nerves in a refrigerator world where a tropical squid would simply shut down and die. Surrounding the colossal squid in this freezing dark is a galaxy of bioluminescence that serves as both a map and a distraction. The deep Southern Ocean is teeming with lanternfish, krill, and comb jellies that produce their own light. To the sensitive eyes of the squid, the darkness is not empty. It is filled with sparks and flashes. The squid must distinguish between the random firing of plankton and the specific rhythmic flashing of its prey. Some researchers believe the colossal squid may use its long tentacles to disturb the water, triggering the bioluminescence of nearby plankton to illuminate potential prey hiding in the dark. It effectively uses the local wildlife as a flashbulb, startling the microscopic sentries into revealing the location of a larger fish, turning the defense mechanism of the plankton against the fish they are trying to protect. The phenomenon known as abyssal gigantism, or deep-sea gigantism, explains why the colossal squid grows to such staggering proportions. In the deep ocean, the water is cold, and the metabolic rate of animals is low. This low metabolism, combined with the high oxygen availability in Antarctic waters, allows animals to grow larger than their shallow water counterparts. Additionally, the scarcity of food favors larger animals that can cover more distance with each swim stroke and store more energy reserves in their bodies. Being big is efficient. A large body retains heat, however little there is, better than a small one, and a large stomach can hold a meal that lasts for months. The colossal squid is the ultimate expression of this rule, a creature that has traded speed and agility for sheer size and endurance, becoming a giant because the physics of the deep favor the massive. Supporting this massive frame is not a skeleton of bone, but a single internal structure known as the gladius, or pen. This is a long, transparent, plastic-like rod made of chitin that runs the entire length of the mantle. It acts as a backbone, providing a rigid attachment point for the muscles and giving the squid its shape. Without the gladius, the squid would be a shapeless sack. In the colossal squid, this pen is incredibly robust, wide, and flexible. It can bend with the movements of the mantle as the squid breathes and swims, but it is stiff enough to prevent the body from collapsing under the drag of the water. When a predator attacks, the gladius protects the vital organs like a shield. It is a remnant of the ancestral shell that mollusks once carried on their backs, now internalized and streamlined into a hidden strut of biological plastic. When the colossal squid feels threatened in the abyss, it employs a defense mechanism that is both classic and uniquely adapted to the dark: the release of ink. However, at these depths, a simple cloud of black dye would be invisible in the black water. Instead, the squid releases a cloud of mucus-bound ink that holds its shape. This is known as a pseudomorph, or false body. The blob of ink is roughly the same size and shape as the squid itself. In the split second that the predator attacks the ink decoy, the real squid turns off its photophores, becoming instantly invisible, and jets away. The high mucus content prevents the ink from dissipating too quickly, creating a tangible phantom that hangs in the water. buying the giant valuable seconds to escape into the silence. The reproductive life of the colossal squid remains one of the greatest unsolved mysteries in marine biology. No human has ever seen them mate. Based on the anatomy of related species, it is believed that the male possesses a specialized arm called the hectocotylus, which is used to transfer packets of sperm, known as spermatophores, to the female. These spermatophores are not microscopic. In giant squid species, they can be the size of a baseball bat. The male likely uses his hydraulic pressure to inject these packets directly into the female's arms or mantle tissue. This traumatic insemination ensures that the sperm is securely delivered. The female then carries the sperm until she is ready to spawn, a silent carrier of the next generation waiting for the perfect chemical cues in the water to release her millions of eggs. Once fertilized, the female likely releases a massive gelatinous egg mass. Unlike shallow water squid that attach their eggs to rocks, deep-sea squid often produce free-floating masses. This sphere of jelly can be several feet across, containing tens of thousands of tiny, transparent eggs. The jelly protects the developing embryos from bacteria and small predators, and it provides buoyancy. This ghost sphere drifts in the deep currents, a silent nursery moving through the bathypelagic zone. The female, having exhausted her immense energy reserves to produce this mass, likely dies shortly after, her body slowly sinking to the seafloor to feed the scavengers, a final act of sacrifice that closes the loop of her life. When the eggs hatch, the babies, known as paralarvae, look nothing like the terrifying adults. They are tiny, perhaps only a few millimeters long, with stubby arms and enormous eyes relative to their bodies. Interestingly, the paralarvae of the colossal squid have a very different appearance from the adults. Their tentacles are fused together into a proboscis, which eventually splits as they mature. These tiny creatures do not live in the deep, they float upward to the surface layers of the ocean. Here, in the slightly warmer, plankton-rich waters, they feed and grow rapidly. They are transparent and defenseless, drifting with the krill, hiding in the sheer volume of the plankton bloom. It is a dangerous infancy, where the future monsters are snacks for seabirds and small fish, surviving only by the law of large numbers. As the paralarvae grow, they undergo a process known as ontogenetic descent. This is a gradual, lifelong migration downward. As the squid gets larger and heavier, it moves deeper into the ocean. A juvenile might live at 500 meters, hunting krill. A subadult moves to 1,000 meters, hunting small fish. Finally, the massive, mature adults settle into the abyssal depths of 2,000 meters or more. This separation of generations prevents the adults from competing with or eating their own offspring. It also means that the squid's life is a long, slow fall into the dark. It is born in the light and dies in the shadow, a trajectory that takes it further away from the sun with every passing month of its life. The beak of the colossal squid is the only part of the animal that is truly indestructible, and it serves as the primary tool for scientists trying to estimate the population. Because the beak is made of hard, cross-linked proteins, similar to a fingernail, but much denser, it resists digestion in the stomachs of predators. Sperm whales consume thousands of squid in their lifetimes, and while the flesh is digested, the beaks accumulate in the whale's stomach. By examining the stomach contents of beached whales, scientists have found thousands of colossal squid beaks. By measuring the rostral length, the size of the lower beak's cutting edge, researchers can mathematically calculate the total size and weight of the squid it came from. These hard, black artifacts are the data points of the deep, durable records of meals eaten in the dark. The chemical composition of this beak is a marvel of gradient material science. At the tip, where it must slice through bone and spine, the beak is incredibly hard and sharp, heavily mineralized and dehydrated. But as you move back toward the muscle attachment points, the material becomes softer and more flexible. This gradient prevents the hard beak from damaging the soft muscular tissue of the mouth when the squid bites down with force. If the beak were uniformly hard, the shock of the impact would tear it loose from the soft body. Instead, the material transitions smoothly from diamond-hard cutting edge to rubbery cartilage, absorbing the shock and distributing the force evenly through the buccal mass. It is a tool that is integrated perfectly into the soft machine that wields it. The digestion of the colossal squid is a process dictated by the laws of thermodynamics in the cold. Because its metabolism is so slow, digesting a large meal like a toothfish can take days or even weeks. The stomach of the squid is a muscular sac lined with ridges that help knead the food. Enzymes break down the proteins into a liquid slurry, which is then absorbed by the digestive gland, a massive organ that functions like a combined liver and pancreas. This gland, often colored orange or brown, occupies a large portion of the mantle cavity. The slow pace of digestion means the squid does not need to hunt every day. A single large kill can sustain it for a long period of quiescence, allowing it to hang in the water and conserve energy while its internal chemistry quietly turns fish into squid. One of the most peculiar anatomical features of the colossal squid, shared with all cephalopods, is the location of its brain. The brain is donut-shaped, a ring of neural tissue that encircles the esophagus. This means that every bite of food the squid swallows must pass through the center of its own brain. This places a strict physical limit on the size of the chunks it can swallow. If it swallows a piece of bone or meat that is too large, it could physically damage its brain or cut off the neural signals. This vulnerability is why the radula is so important. It acts as a garbage disposal, grinding the food into a fine paste that can safely slide through the neural ring. It is a precarious design flaw that demands careful eating, forcing the monster to be a meticulous diner. Deep inside the head, near the brain, are two tiny, stone-like structures called statoliths. These are the squid's ear bones, essential for balance and orientation. They are made of calcium carbonate and grow by accumulating layers of material every day, much like the rings of a tree. By slicing these microscopic stones and counting the daily rings, scientists have discovered a shocking fact about the colossal squid's life history. They grow incredibly fast. Despite reaching half a ton in weight, these animals likely only live for about 2 years. This growth rate is astronomical, one of the fastest in the animal kingdom. They are the drag racers of biology, converting energy into mass at a breakneck speed, rushing toward a massive adulthood, only to die shortly after reproducing. This short lifespan creates a population turnover that is rapid and dynamic. The colossal squid does not linger for decades like the whales that hunt it. The entire population of adult squid is replaced every 2 to 3 years. This means the biomass of the deep ocean is in constant flux. In years where food is plentiful, the squid grow larger and more numerous. In lean years, they may be smaller. This rapid cycle makes them highly responsive to environmental changes. They are the weeds of the deep sea, fast-growing, opportunistic, and resilient. A single generation can reset the ecological stage, quickly filling the void left by their parents. Finally, the relationship between the colossal squid and the wandering albatross provides a connection between the deepest ocean and the highest sky. Albatrosses are surface feeders. They cannot dive deep. Yet, their stomachs often contain the beaks of colossal squids. This paradox was solved when scientists realized that the squids, after spawning, become buoyant and float to the surface to die. This is known as post-spawning float. The dying giants, their bodies degrading and turning white, drift on the waves of the Southern Ocean. The albatrosses, with their immense wingspans, spot these white shapes from miles away. They land and scavenge the carcass, feasting on the flesh of a creature that lived its entire life in darkness, only to be consumed in the bright, freezing wind of the surface. It is a transfer of energy from the abyss to the air, linking the monsters of the deep to the wanderers of the clouds. The mechanics of the colossal squid's weaponry are far more sophisticated than simple grasping. The swiveling hooks that line its arms are marvels of biological engineering, designed for a world where friction is the only thing standing between a meal and starvation. Unlike the static claws of a cat or the fixed teeth of a shark, the hooks of the colossal squid are embedded in muscular pedestals that allow them to rotate. Each hook is a curved scimitar of hard chitin, encased in a sheath of white, fleshy tissue. When the arm is relaxed, the hooks can lay flat or retract slightly, minimizing drag as the squid swims. But when the muscles contract upon contact with prey, the hooks stand erect and can pivot to find the point of least resistance in the prey's flesh. This swiveling action ensures that no matter how the toothfish thrashes or spins, the hook moves with it, digging deeper rather than tearing free. It is a dynamic grip, a clutching mechanism that adjusts in real time to the struggles of the victim, turning the chaotic energy of the escape attempt into the very force that secures the bond. Complementing these hooks on the tentacular clubs is a feature known as the carpal lock, or the fixing apparatus, which transforms the two long tentacles into a single, unified weapon. The tentacles are usually deployed separately to snatch prey, but for a heavy load, the squid needs leverage. At the base of the club, where the tentacle meets the hooks, there is a specialized section of suckers and knobs that act like a biological zipper. The knobs on the left tentacle fit perfectly into the suckers on the right tentacle, and vice versa. When the squid presses these sections together, they lock with a seal so tight that they essentially fuse into a single rigid bar. This locking allows the squid to synchronize the pull of both tentacles, doubling the force applied to the prey without requiring the muscles to actively hold the limbs together. It creates a stable platform for the hooks to do their work, a momentary fusion of limbs that allows the squid to haul massive weight through the water with the efficiency of a winch. The propulsion system of the colossal squid relies on a structure called the funnel, or siphon, a muscular tube located on the underside of the mantle that functions as a vector thrust engine. The squid draws water into its mantle cavity to breathe, and then, by contracting the powerful circular muscles of the mantle wall, it forces that water out through the funnel under immense pressure. The funnel is mobile and can be aimed in almost any direction. To swim backward, the squid's fastest mode of travel, it points the funnel forward, blasting a jet of water past its head. To hover or inch forward, it points the funnel backward. This directional control allows the massive animal to maneuver with surprising agility, turning in its own length or holding its position against a deep-sea current with subtle puffs of water. It is a jet engine made of flesh, intake, and exhaust, combined into a single, rhythmic cycle of breath and motion. To withstand the immense internal pressure generated during this jet propulsion, the colossal squid possesses a locking mechanism that secures its head to its body, known as the nuchal cartilage. At the back of the squid's neck and on the inner surface of the mantle, there are matching grooves and ridges made of dense, gristly cartilage. When the squid prepares to jet, these cartilages slide together and lock, effectively clamping the heavy head and arms to the mantle. This prevents the head from being blown off or destabilized by the violent expulsion of water. It effectively turns the soft, multi-part body into a rigid, hydrodynamic missile for the duration of the sprint. When the jet is finished, the lock disengages, allowing the head to move freely again. It is a safety latch for high-speed travel, ensuring the animal stays in one piece when it exerts its maximum power. The nervous system that controls these explosive movements is built for speed in the cold, relying on structures known as giant axons. In the freezing temperatures of the Antarctic, nerve impulses naturally travel slower. To compensate for this thermal delay, the colossal squid, like many cephalopods, has evolved nerve fibers of exceptional thickness. The diameter of a nerve axon is directly proportional to the speed at which it conducts electricity. The giant axons running to the mantle muscles are thick white cords, visible to the naked eye. They allow the signal from the brain to reach the muscles at the far end of the mantle in a fraction of a second, triggering a synchronized contraction. Without these biological fiber optic cables, the squid's reaction time would be sluggish, leaving it vulnerable to the lightning-fast strikes of sperm whales. It is a hardwired solution to the physics of the cold, a high-bandwidth network running through the gelatinous body. Sharing the freezing darkness with the colossal squid is a rival that is nearly as large but often overlooked, the warty squid, Condacovia longimana. This massive cephalopod grows to lengths of over 7 feet and competes directly with the colossal squid for food and territory. The Condacovia gets its name from the microscopic, rough bumps on its skin, which give it a texture like sandpaper, unlike the smooth skin of the colossal. While the colossal squid relies on hooks, the warty squid relies on power and suction. Isotope analysis of their tissues suggests they occupy slightly different niches, with the warty squid feeding more on krill and smaller prey, while the colossal targets the top-tier fish. However, in the nutrient-limited depths, their paths undoubtedly cross. We can imagine the silent, slow-motion turf wars that occur in the abyss. Two giants drifting past one another, assessing the threat, divided by the texture of their skin and the specific curve of their beaks. The geographical range of the colossal squid is strictly bounded by an invisible wall of water known as the Antarctic convergence. This is a circumpolar front where the freezing, northward-flowing waters of Antarctica meet the warmer, sub-Antarctic waters of the Atlantic, Pacific, and Indian Oceans. The temperature difference creates a biological barrier that the colossal squid rarely crosses. It is an endemic species, meaning it lives only in the southern oceans south of this line. The physiological reliance on cold water for its metabolism and blood chemistry traps it there. If a colossal squid were to drift north across the convergence, the warmer water would likely cause its metabolic rate to spike uncontrollably, and its ammonia buoyancy system might become unstable. It is a prisoner of the pole, locked in the freezer of the world by the thermodynamics of its own body. The male colossal squid is a figure of biological obscurity, significantly smaller than the female, and rarely seen by human eyes. This extreme sexual dimorphism is common in deep-sea giants. The female needs to be massive to produce and carry the enormous volume of eggs required to ensure survival, acting as a living ark. The male, by contrast, needs only to be mobile and fertile. His life is a frantic search for a mate in the vast, empty dark. Because he is smaller, he is faster and more agile, but he lives in constant danger of being eaten by the female. The mating encounter is likely a tense, dangerous event where the male must approach the giant female, deliver his genetic payload, and retreat before he triggers her predatory instincts. It is a romance of disparate scales, where the difference in size defines the dynamic of the relationship. The spermatophores carried by the male are not microscopic cells, but complex biological devices that function like hypodermic needles. These packets of sperm are equipped with an ejaculatory apparatus. When the male transfers them to the female, a chemical trigger causes the spermatophore to fire, driving a cement body and the sperm mass directly into the female's tissue. This process, known as deep tissue implantation, leaves visible scars on the female's skin, Examination of captured females often reveals small, white, fibrous patches on their mantles or arms, the healed wounds of mating. The sperm is stored deep within the muscle or in specialized receptacles, waiting for the moment of spawning. This aggressive method ensures that the sperm is not washed away by the currents, physically embedding the future generation into the mother's flesh. Inside the funnel of the squid lies a specialized sensory structure called the funnel organ, or the organ of Verrill. This glandular patch of tissue looks like a W-shaped ridge. Its function is to detect the chemical composition of the water passing through the siphon. It acts as a taste tester for the respiratory stream. As the squid breathes, the funnel organ constantly samples the water for the scent of prey, the pheromones of a mate, or the chemical signature of a predator. It allows the squid to smell the water it is swimming through without interrupting its breathing rhythm. In the pitch black, where eyes are only useful for spotting bioluminescence, this chemical scanner provides a continuous stream of environmental data, sniffing the currents for the faintest trace of organic molecules. The optic lobes of the colossal squid's brain are kidney-shaped masses of neural tissue that are enormous relative to the rest of the brain, reflecting the animal's reliance on vision. These lobes process the signals from the massive eyes. However, despite the size of the eyes, the colossal squid is likely colorblind. Most deep-sea animals possess only a single visual pigment, tuned to detect blue light, which is the only wavelength that penetrates deep water and the color of most bioluminescence. Seeing in color requires multiple pigments and reduces overall sensitivity. By sacrificing color vision, the squid gains contrast sensitivity. It sees the world in high-resolution monochrome, detecting the silhouetted edges of prey against the faint background glow. It does not need to see the red of a shrimp or the silver of a fish. It only needs to see the shadow that breaks the pattern of the dark. The specific identification of colossal squid beaks found in whale stomachs relies on a distinct architectural feature, the rostral notch. On the lower beak of the squid, there is a prominent fold or groove that is absent in the giant squid. This notch helps specialized muscles attach to the beak, allowing for a stronger shearing action. Paleontologists and marine biologists look for this specific curve in the hard, black chitin to distinguish the colossal from the giant. It is a fingerprint in bone-like material. These beaks can persist in the environment for years, eventually settling into the sediment. Future geologists might find layers of these beaks in the fossil record of the Southern Ocean, a geological stratum made of the mouthparts of monsters, marking the era when the Antarctic was ruled by cephalopods. The ammonia that provides buoyancy to the squid is not evenly distributed. It is concentrated in specialized vacuoles within the muscle cells, separating it from the blood supply to prevent toxicity. Ammonia is toxic to living tissue at high concentrations. The squid has evolved a cellular architecture that quarantines this fluid, using pH gradients to keep it contained. This adaptation turns the squid's entire body into a flotation device, but it makes the animal chemically fragile. If the squid is brought to the surface quickly, the pressure drop can cause these vacuoles to rupture, releasing the ammonia into the rest of the tissues and effectively pickling the animal from the inside out. This is one reason why captured specimens are often in poor condition. Their own buoyancy fluid destroys them as they ascend. The texture of the colossal squid's skin is markedly different from the smooth, slick skin of shallow water squids. It is often described as having a gelatinous, almost dissolving quality when brought to the surface. This is due to the breakdown of the collagen matrix that holds the skin together. In the high-pressure, cold environment of the deep, the collagen is stable. But at surface pressure and temperature, the protein structure loses its integrity. The skin sloughs off easily, leaving the raw white mantle exposed. This fragility has made studying the external anatomy difficult, as nets and lines often strip the animal of its outer layer. The monster we see on the deck of a ship is a melting version of the creature that exists in the deep, a ghost that loses its form when removed from the pressure that defines it. The role of marine snow in the deep ocean ecosystem is the foundation of the colossal squid's empire. Marine snow consists of dead plankton, fecal pellets, and organic dust falling from the surface waters. This constant rain of nutrients feeds the copepods, which feed the krill, which feed the toothfish, which feed the squid. The colossal squid is, therefore, the apex collector of this falling energy. Every atom in its 1,000-pound body ultimately drifted down from the sunlit world in the form of microscopic flakes. The squid is a massive reservoir of recycled surface life, a dark storage tank for the carbon that was fixed by algae miles above its head. When the squid dies and sinks, it returns this carbon to the seabed in a massive pulse, completing the cycle. The historical confusion between the colossal squid and the kraken of Norse mythology is a case of mistaken latitude. The kraken is typically associated with the giant squid, Architeuthis dux, of the North Atlantic. The colossal squid lives only in the Antarctic, a region unknown to the Vikings. However, the legends share a common root in the primal human fear of the tentacled deep. The descriptions of the kraken, a creature so large it was mistaken for an island, capable of dragging ships down, resonate with the sheer bulk of the colossal squid. If a Viking had ever sailed far enough south to encounter a dying colossal squid floating on the surface, its width and heavy hooks would have undoubtedly confirmed their darkest nightmares, adding a new chapter of frozen terror to the saga of the sea monsters. The decomposition of a colossal squid carcass in the deep ocean is a slow, cold process that creates a temporary ecosystem known as a cephalopod fall. Unlike a whale fall, which has heavy bones, the squid is soft tissue and chitin. Scavengers like amphipods, sleeper sharks, and hagfish arrive quickly. Because the flesh is ammoniacal, not all scavengers can eat it. It requires specialized metabolic adaptations to process the ammonia-tainted meat. The beak and the pen take the longest to degrade. For a few weeks, the carcass is a hub of activity in the silent plains, a white bonanza that draws the blind, smelling creatures of the abyss out of the mud to feast on the giant that has finally fallen from the water column. The auditory world of the colossal squid is one of low-frequency vibrations. Water conducts sound 5 times faster than air, and low-frequency sounds travel for thousands of miles. The breaking of ice shelves, the grinding of icebergs, and the calls of blue and fin whales create a constant, low-rumble background noise in the Southern Ocean. The squid lacks gas-filled ears, so it does not hear sound pressure like we do. Instead, its statocysts detect the particle motion of the water, the physical displacement caused by the sound wave. It feels the noise. The approach of a large predator, like a sperm whale, creates a rhythmic pressure wave that the squid can detect long before the whale's sonar clicks are audible, giving it a warning tremor in the dark. The terminal spawn hypothesis suggests that female colossal squids invest so much energy into their single reproductive event that they biologically disintegrate afterwards. This is a common strategy in cephalopods called semal parity. The female converts her muscle mass into egg production. Her digestive gland shrinks, her muscles atrophy, and her immune system shuts down. She becomes a living husk, dedicated entirely to the synthesis of the next generation. By the time she releases her egg mass, she is a ghost, incapable of hunting or healing. This strategy ensures the maximum possible number of eggs are produced, but it means there are no wise elders in the squid world. Every adult you see is a first-time parent on the verge of death, a tragic biological sprint to the finish line of life. The difficulty of studying these animals alive has led to the freezer approach to science. Almost every specimen of a colossal squid in a museum today arrived there as a frozen block of ice. They are caught by fishing boats, frozen in the hold to preserve them, and then thawed out months later in a laboratory. This freezing process damages the delicate eyes and tissues, turning the clear lenses opaque and the skin grey. Scientists essentially perform autopsies on ice lollies. This means our understanding of their physiology is largely reconstructed from dead, damaged tissue. We have never seen a colossal squid displaying its natural colours, flashing its photophores, or moving with its natural grace. We know the monster only as a corpse, a frozen echo of the living, breathing giant that rules the underside of the world. The relationship between the colossal squid and the Antarctic toothfish is not merely predator and prey. It is a central pillar of the entire Southern Ocean ecosystem, a transfer of energy that dictates the flow of life in the deep. When a squid consumes a toothfish, it is absorbing years of accumulated energy. Toothfish are long-lived, slow-growing animals that can reach 50 years of age. They are reservoirs of calories. By eating them, the squid is concentrating decades of Antarctic productivity into a single, massive body. This energy concentration makes the squid a keystone resource for the sperm whales. If the squid were removed, the whales would have to hunt thousands of smaller fish to get the same caloric intake as one squid provides. The squid acts as a biological battery, storing the slow, cold energy of the fish in a high-density package that fuels the warm-blooded giants of the surface, linking the slow rhythm of the fish to the fast rhythm of the whale. The depth at which the colossal squid lives protects it from one of the ocean's most pervasive threats: ultraviolet radiation. In the clear waters of the Antarctic, UV light can penetrate surprisingly deep, damaging DNA and blinding larval fish. But below 500 meters, the water is eternally safe from this radiation. The squid's massive eyes, sensitive enough to detect a single photon, would be instantly damaged by sunlight. This sensitivity traps the squid in the dark. It lives behind a permanent curtain of water that filters out the harmful rays of the sun. If a colossal squid were brought to the surface during the day, the light would likely burn its retinas, blinding it even if the pressure change didn't kill it. It is a creature of the shadows, protected by the very water that obscures it from our view. Deep within the mantle cavity, the colossal squid possesses a pair of nidamental glands that play a crucial role in the production of its egg mass. These large white organs secrete the gelatinous matrix that surrounds the eggs, but they also house a symbiotic community of bacteria. In other squid species, these bacteria produce antifungal and antibiotic chemicals that protect the eggs from disease. It is highly likely the colossal squid shares this adaptation. The mother squid is essentially culturing a pharmacy inside her own body. When she lays her eggs, she coats them in this bacterial slime, inoculating her offspring against the pathogens of the deep. This chemical defense allows the egg mass to drift for months without rotting, a sterile bubble of life floating in a sea of decay. The colossal squid's role in the carbon cycle includes a phenomenon known as the squid pump. When the squid feeds at depth and releases waste, or when it dies and sinks, it transports carbon from the upper ocean to the deep sea floor. This sequestration is vital for regulating the planet's climate. The carbon contained in the body of a half-ton squid is effectively removed from the atmosphere for centuries, once it is buried in the abyssal mud. Because of their fast growth and high biomass, These squids are major players in the biological pump of the Southern Ocean. They are silent climate engineers, locking away the greenhouse gases of the industrial world in their gelatinous tissues and carrying them down to the bottom of the world where they can do no harm. The sensory tentacles of the colossal squid are equipped with distinct clusters of suckers at the tips, separate from the hooks. These suckers are covered in tiny, sensitive bristles that act as taste buds. Before the squid commits to striking with its hooks, it may gently touch the prey with these tips to taste it. This tactile tasting allows the squid to differentiate between a rock and a sleeping fish, or between a palatable species and a toxic one. In the pitch black, touch and taste are fused into a single sensation. The squid feels the chemical signature of the object, making a split-second decision to attack based on the flavor of the skin it is touching, a gourmet of the gloom selecting its meal by the texture of the molecules. In the 19th century, sailors often reported seeing sea serpents fighting whales in the Southern Ocean. These accounts described massive, snake-like coils wrapping around the whales. We now understand these were likely sightings of sperm whales battling colossal squids at the surface. When a whale forces a squid to the surface, the squid's tentacles flail wildly. To a sailor on a wooden ship, seeing a 30-foot limb writhing around a whale's jaw would look exactly like a serpent. The head of the serpent was the club of the tentacle. These myths were simply misinterpretations of a biological reality that was too strange for the Victorian mind to categorize, turning a cephalopod into a dragon to make sense of the violence in the water. The ink sac of the colossal squid is buried deep within the digestive gland, a location that protects it from accidental rupture. The ink itself is almost pure melanin, the same pigment that colors human skin and hair. This high concentration of melanin makes the ink incredibly viscous and dark. It is also rich in dopamine and L-dopa, chemicals that can disrupt the sensory systems of predators. When a sperm whale swims through a cloud of this ink, the chemicals may temporarily numb its sense of smell or taste, or irritate its sensitive eyes. The ink is not just a visual screen, it is a chemical weapon, a cloud of narcotic darkness, designed to confuse the attacker on a neurological level, while the squid makes its escape. The hydrostatic skeleton of the colossal squid relies on the incompressibility of water to maintain its shape. The squid has no bones to push against. Instead, its muscles are arranged in opposing layers. Circular muscles wrap around the mantle, and radial muscles run through the wall. When the circular muscles contract, the mantle lengthens. When the radial muscles contract, the mantle wall thins and expands. This hydraulic system allows the squid to change its shape instantly. It can become long and thin to reduce drag, or short and wide to flush water. It is a machine made of pressurized fluid, using the ocean inside its own cells to create the leverage needed to move the ocean outside. The beak wars of the deep sea refer to the competition between the colossal squid and the giant squid. While their ranges overlap slightly, they generally stay apart. The giant squid prefers the temperate waters, while the colossal rules the polar seas. This geographic separation prevents direct competition. However, in the boundary zones, like the waters off New Zealand, they may encounter each other. The colossal squid, being heavier and armed with hooks, would likely dominate a physical confrontation. It is the heavyweight wrestler to the giant squid's lanky boxer. The ocean has partitioned these two monsters into separate kingdoms of cold and cool, ensuring that the two largest invertebrates on Earth rarely have to fight for the same throne. The specialized collar muscles of the colossal squid act as a seal for the mantle cavity. These muscles lock the mantle to the head, ensuring that water can only escape through the siphon and not leak out the front. This seal must be watertight to generate the pressure needed for jet propulsion. The locking cartilages we discussed earlier are the mechanical latches, but the collar muscles are the gasket. They must maintain a perfect seal even when the squid is contorting its body. If this seal fails, the jet loses power and the squid becomes sluggish. It is a biological O-ring, a ring of muscle that keeps the engine pressurized and the animal moving. The decomposition of the colossal squid's eyes after death reveals a structural secret. The lens breaks down into two distinct hemispheres. This suggests that the lens is formed from two separate developmental plates that fuse together. This bipartite structure may help correct for spherical aberration, a visual distortion common in simple lenses. By constructing the lens from two halves with different refractive indices, the squid can bring light to a sharper focus on the retina. It is a natural corrective optic, a bifocal design built into the eye to ensure that the image of a bioluminescent lure in the distance is crisp and clear, allowing the predator to judge the distance perfectly. The colossal squid is a terminal spawner, meaning it reproduces once and then dies. This life history strategy, known as semal parity, is a high-stakes gamble. The squid invests every ounce of energy it has into a single reproductive event. It does not hold anything back for survival or healing. This means there are no experienced mothers in the population. Every female laying eggs is doing it for the first time. The entire knowledge of the species, how to hunt, where to hide, how to mate, is transmitted genetically, not socially. There is no learning from elders because the elders are dead. It is a lonely lineage where every generation is an orphan, guided only by the instinct written in the code of its DNA. The mystery of the gelatinous consistency of the colossal squid's flesh led early researchers to believe it was a slow, weak swimmer. They assumed that mushy meant lazy. However, recent biomechanical studies have shown that the collagen fibers in the mantle are arranged in a cross-helical pattern, like the ply of a tire. This structure allows the soft tissue to store elastic energy. When the mantle expands, the collagen stretches like a rubber band. This stored energy helps the mantle snap back during contraction, powering the jet. The squid is not mushy, it is spring-loaded. Its soft body is a highly efficient energy storage device that allows it to pulse through the water with a power that belies its texture. The geographic isolation of the Southern Ocean acts as a genetic bottleneck for the colossal squid. Because the Antarctic circumpolar current is such a strong barrier, the population is genetically contained. This lack of mixing with outside squid lineages has allowed the colossal squid to evolve its unique traits, the hooks, the size, the antifreeze, without dilution. It is an evolutionary laboratory isolated by a wall of current. The colossal squid is the result of millions of years of solitary refinement in the coldest room of the world, a unique experiment in gigantism that could only happen in the isolation of the Antarctic ring. The buccal membrane is a web of skin that connects the bases of the arms, forming a small canopy around the mouth. In the colossal squid, this membrane is dark purple or black. Its function is not fully known, but it may act as a trap or a funnel. When the arms pull prey toward the mouth, the membrane expands to prevent the fish from slipping out between the arms. It creates a seal around the victim. It may also contain sensory cells to taste the food before it enters the beak. It is the final curtain, a dark web that encloses the prey in the moment before consumption, ensuring that once a fish enters the circle of arms, the only exit is down the throat. The colossal squid's tentacles are capable of regeneration, though the process is slow. If a tentacle is severed in a battle with a sperm whale, the squid can regrow it. However, because the animal's lifespan is so short, it is unlikely that a regenerated tentacle would ever reach full size or functionality before the squid dies. A squid with a missing tentacle is at a severe disadvantage. It loses its long-range strike capability, and must rely on its shorter arms, forcing it to get closer to prey and exposing it to greater danger. The scars and missing limbs found on captured specimens are the battle damage of a war, where healing is a luxury the combatants cannot afford. The statosis dance is a theoretical behavior where the squid might use its balance organs to detect the infrasound of approaching whales. Sperm whales produce powerful, low-frequency clicks that can stun prey, but they also create pressure waves as they swim. The statocysts of the squid are sensitive to these low-frequency vibrations. The squid might be able to hear the displacement of the water caused by the whale's body long before the sonar clicks become dangerous. This would give the squid a few minutes of warning to go silent, turn off its photophores, and drift into the acoustic shadow of a thermal layer to hide. The interaction between the colossal squid and the Antarctic toothfish fishery is a source of conflict and data. Fishermen view the squid as a thief. The squid has learned that the long lines set by humans are free buffets. It will swim along the line, plucking the hooked toothfish off one by one. This behavior, known as depredation, is dangerous for the squid. It risks getting hooked itself. But it also provides the only opportunity for scientists to study fresh specimens. Almost every colossal squid in a museum was caught because it tried to steal a lunch from a fishing boat. The human appetite for sea bass is the primary reason we know anything about the appetite of the squid. The beak notch, found on the lower mandible of the colossal squid, is a specific adaptation for shearing the spine of the toothfish. The notch fits perfectly over the vertebrae of the fish. When the beak closes, the notch acts like a wire cutter, snapping the bone cleanly. This prevents the beak from slipping off the round bone. It is a specialized tool evolved for a specific job. The geometry of the beak is a mirror of the anatomy of its prey, a lock and key relationship where the key is a blade designed to unlock the meat from the bone. The sheer volume of water pumped by the colossal squid's gills is enormous. To extract enough oxygen from the cold water to support a half-ton body, the squid must process thousands of liters of water per hour. The mantle cavity is a high-volume pump. This constant flow of water also serves to clean the gills and the mantle of waste and parasites. The squid is constantly flushing itself with the ocean. It lives in a river of its own making, a continuous stream of Antarctic water that enters the collar and exits the siphon, carrying the breath of life and the jet of motion in a single, ceaseless cycle. The isolation of the colossal squid is not just geographic, but acoustic. It lives in a world where sound is the primary medium of information, yet it possesses no ears to hear it. Unlike whales or fish that have otoliths or gas bladders to detect sound pressure, the squid relies entirely on the statocysts we discussed earlier to feel the particle motion or the physical displacement of water caused by a sound wave. This means the colossal squid lives in a world of vibration rather than tone. It feels the thrum of a ship's engine or the rhythmic beat of a whale's tail as a tactile sensation, a trembling in the water that vibrates the stones in its head. This sense is directional but short range. The squid is deaf to the long-distance songs of the whales that hunt it, only becoming aware of the predator when the water itself begins to shake with the proximity of the Leviathan's approach, a silent horror movie where the monster is felt before it is heard. The metabolic strategy of the colossal squid involves a physiological trade-off known as the PO ratio, which dictates how efficiently its cells convert oxygen into energy. In the freezing, oxygen-rich waters of the Antarctic, the squid has evolved to prioritize efficiency over power. Its mitochondria, the power plants of the cells, are tuned to run at a low idle. This allows the squid to survive long periods of starvation. A colossal squid can likely go for months without eating, drifting in a state of metabolic torpor, where its hearts beat only a few times a minute. This suspended animation is crucial in the deep sea where meals are infrequent. The squid is not a constantly running engine. It is a battery that sits on the shelf, holding its charge for the singular moment when a fish swims by, exploding into action before returning to the long, cold wait. The mantle locking apparatus is a feature of the colossal squid's anatomy that prevents it from blowing itself apart during jet propulsion. When the mantle contracts to force water out of the funnel, the internal pressure is immense. Without a way to secure the head to the body, the force of the water could decapitate the squid or cause the mantle to slide backward. To prevent this, the squid has 3 distinct locking cartilages, 1 on the back of the neck, the nutshell lock, and 2 on the sides of the funnel. These cartilages fit into corresponding grooves on the mantle wall like a tongue and groove joint. When the squid jets, these locks engage, fusing the separate parts of the body into a single, rigid unit. It is a biological safety latch that ensures the structural integrity of the animal when it needs to move fast, turning a soft-bodied mollusk into a solid, pressurized rocket. In the deep ocean, the oxygen minimum zone acts as a vertical barrier for many animals, but the colossal squid navigates it with ease due to its unique blood chemistry. Between 200 and 1,000 meters, the decomposition of organic matter consumes most of the oxygen in the water. Fast-moving fish like tuna cannot survive here, but the colossal squid, with its hemocyanin-based blood and low metabolic rate, can thrive in this suffocating layer. It uses the oxygen minimum zone as a refuge. It can hide there to digest its food or escape from air-breathing predators like whales and seals, which cannot linger in the deep for long. The low oxygen levels suppress the activity of its prey, making them lethargic and easier to catch. The squid is the king of the breathless zone, ruling the layer of the ocean where other animals gasp and die. The rostral vibration hypothesis suggests that the colossal squid might use its beak to produce sound. While cephalopods are generally mute, some researchers believe they can grind their beaks together to create a clicking or rasping noise. In the deep ocean, sound is a way to startle predators or attract mates. If the colossal squid were to grind its massive, hard beak, the sound would be a loud, cracking click that would travel far in the water. This could serve as a warning signal, a way to tell a rival squid to back off, or perhaps a mating call in the absolute darkness. While unproven, the idea of the silent dark being broken by the rhythmic clacking of giant beaks adds a haunting acoustic layer to our understanding of the abyss. The sheer thickness of the colossal squid's mantle wall is a defense mechanism against the crushing teeth of its predators. In some places, the muscle of the mantle is several inches thick. This is not just for propulsion, it is armor. When a sperm whale bites a squid, it must bite through this dense, rubbery muscle to reach the vital organs. The thickness of the mantle protects the hearts and the brain. Furthermore, the ammonium chloride in the tissue makes the flesh taste bitter and repulsive. A predator that takes a bite might be discouraged by the taste and the texture, spitting the squid out. The squid is built to be difficult to chew and unpleasant to swallow, a survival strategy based on being the most unappetizing item on the menu. The visual system of the colossal squid is so advanced that it likely processes polarized light. In the ocean, light becomes polarized. The light waves align in a specific direction. Many marine animals use polarization for camouflage, hiding their silhouettes. But cephalopods are masters of detecting this hidden dimension of light. The structure of the retina in the colossal squid suggests it can see patterns of polarization that are invisible to humans and whales. This allows it to break the camouflage of silvery fish like the toothfish, which reflect polarized light. To the squid, the invisible fish glows against the background. It is a form of X-ray vision that strips away the hiding strategies of its prey, revealing the truth of the water column in high contrast detail. The funnel valve, located inside the siphon of the squid, is a simple flap of tissue that prevents water from flowing backward into the mantle during inhalation. This acts as a one-way check valve. It ensures that the flow of water is unidirectional, in, through the collar, out through the siphon. This efficiency is vital for the energetics of swimming. If water leaked back in through the siphon, the jet would lose power. The valve is a small, unglamorous flap, but it is critical for the propulsion of the 1,000-pound animal. It is a piece of plumbing evolved to perfection, ensuring that every contraction of the mantle translates into forward motion without waste. The chromatophore pulse is a theoretical behavior where the colossal squid might flash its skin color rapidly to confuse prey or predators. While deep-sea squid are generally red, they still possess the neuromuscular organs to change color. In a confrontation with a sperm whale, the squid might ripple waves of dark and light across its massive body. In the dim bioluminescent environment, this would create a confusing, shifting pattern that breaks up the squid's outline. It might look like a cloud of ink or a swarm of smaller animals. This psychedelic defense would buy the squid a fraction of a second to deploy its hooks or jet away, using the confusion of the eye to escape the hunger of the whale. The decomposition of a colossal squid beak on the seafloor takes decades, serving as a long-term record of the ocean's history. These beaks are made of chitin, a polymer similar to plastic in its durability. They accumulate in the sediment of the Southern Ocean. By taking core samples of the mud, scientists can find beaks from centuries ago. Analysis of the isotopes in these ancient beaks can tell us about the water temperature and the diet of the squid hundreds of years in the past. They are black data chips buried in the mud, holding the environmental history of Antarctica in their chemical structure, waiting to be read by the geologists of the future. The terminal hook on the tentacle club is often the largest and most curved, acting as the primary anchor. Once this hook sinks into the flesh of a fish, it acts as a pivot point. The squid can then swing its tentacle around, wrapping the rest of the club onto the prey to engage the other hooks. It is the first point of contact in a violent interaction. The geometry of this hook is perfect for piercing tough skin. It is not a fishing hook designed to catch a lip. It is a gaff designed to hold a heavy weight. The entire success of the hunt depends on the sharpness and strength of this single point of chitin. The statolith rings of the colossal squid act not just as a calendar of age, but as a thermometer of the past. The width of the daily growth rings on the earstones is influenced by water temperature. A wide ring means warmer water and faster growth. A narrow ring means colder water. By reading the rings of a captured squid, scientists can reconstruct the temperature profile of the water the squid swam through every day of its short life. It is a biological flight recorder. We can trace the vertical migrations and the seasonal movements of the animal just by looking at the stone in its head, mapping its journey through the invisible thermal layers of the Southern Ocean. The vulnerability of the colossal squid to ocean acidification is a looming threat to the species. As the ocean absorbs carbon dioxide, the pH drops and the water becomes more acidic. This acidity attacks calcium carbonate, the material used to make the statoliths. If the statoliths dissolve or form improperly, the squid loses its sense of balance. It would become dizzy, unable to tell up from down, and unable to hunt. The stones in its head are its gyroscope. If they melt, the giant falls. This invisible chemical change in the water poses a greater threat to the colossal squid than any whale, attacking the microscopic foundations of its orientation in the dark. The spermatania are the sperm packets implanted by the male into the female, and they have a mechanism that is almost parasitic in nature. Once injected into the female's tissue, the packet dissolves its outer coating and releases enzymes that allow the sperm to burrow deeper into the muscle or into the body cavity. This ensures that the sperm is not lost. The female carries these burrowing packets for weeks or months. It is a biological burden, a foreign genetic invader that she must tolerate until spawning. The male literally forces his contribution into the female's body, a reproductive strategy that prioritizes the survival of the genes over the comfort of the mother. The buccal palps are small, finger-like projections around the mouth of the squid that help manipulate food. In the colossal squid, these palps are sensitive and muscular. They act as the final hands that position the food for the beak. After the arms have pulled the prey in, the palps take over, turning the chunk of meat so that the beak can slice it at the correct angle. They ensure that no bone or scale jams the mechanism. They are the fine motor tools of the feeding process, working in the shadow of the massive hooks to ensure the smooth processing of the meal. The collagen turnover in the mantle of the colossal squid is incredibly high, allowing it to grow at such a rapid rate. Collagen is the structural protein that holds the body together. To grow from a tiny paralarva to a 10-meter giant in 2 years, the squid must synthesize collagen constantly. This requires a massive intake of protein. The squid is a factory for turning fish protein into squid collagen. This rapid synthesis makes the tissue soft and watery compared to the slow-growing muscle of a fish. It is cheap tissue, built fast and loose to reach a massive size quickly, prioritizing bulk over density in the race to become a giant. The interactions between the colossal squid and the Antarctic toothfish fishery have created a unique depredation behavior that demonstrates learning. The squids have learned that the sound of a boat engine means food. They congregate around the long-lining vessels, waiting for the lines to be hauled up. This behavior is learned, not instinctual. It suggests a level of cognitive flexibility. The squid are solving a problem: how to get food with less effort by exploiting human activity. They are robbing the nets of the apex predator of the surface, a dangerous game of theft that proves the monster of the deep is capable of adapting to the Anthropocene. The eye shine of the colossal squid is not just for camouflage. It may also be used for intraspecific communication. In the darkness, the photophores on the eyes could be flashed to signal other squids. A specific pattern of flashes could indicate aggression, submission, or sexual readiness. Since they live at such low densities, finding a mate is hard. A light signal that travels for hundreds of meters would be a beacon in the dark. The monsters might be talking to each other with their eyes, signaling across the abyss with a language of cold light that we have yet to decipher. The trophic cascade caused by the removal of colossal squids would destabilize the entire Southern Ocean. If the squids disappeared, the population of toothfish might explode, consuming all the smaller fish and krill. The sperm whales would lose their primary food source and might starve or migrate away. The ecosystem is balanced on the back of the squid. It is the central knot in the food web, holding the top and the bottom together. Its existence ensures the flow of energy from the plankton to the whales. It is a keystone species of the highest order, a giant that holds the roof of the Antarctic ecosystem up with its 8 arms. The hydrodynamic wake of a swimming colossal squid is minimal due to its efficient fin motion. Unlike a jetting squid that creates a turbulent plume, the undulation of the fins creates a smooth, laminar wake. This allows the squid to move without creating a pressure shout that would alert prey. It slips through the water. The massive body displaces water, but the fins smooth out the disturbance. It is a stealth bomber of the deep, a massive object moving with a small footprint, gliding through the darkness without disturbing the silence of the water. The final mystery of the colossal squid is the location of its spawning grounds. We have never found a mass of eggs or a gathering of spawning adults. The Southern Ocean is vast and ice-covered. it is likely that the squids spawn deep under the permanent ice shelves, in the most inaccessible places on Earth. They retreat to the hidden fortresses of the Antarctic to reproduce, protecting their vulnerable eggs with a ceiling of ice. This secrecy ensures the survival of the next generation. The giant comes from the unknown and returns to the unknown, leaving us only with the artifacts of its existence, the beaks, the hooks, and the scars, to prove that it was ever there at all. And finally, we drift away from the freezing, heavy waters of the Southern Ocean, leaving the colossal squid to its silent vigil in the dark. We have traveled to the bottom of the world to find a creature that embodies the mystery of the deep, a giant that grows fast, lives slow, and dies young, hidden beneath the ice and the waves. It is a monster only in size. In reality, it is a marvel of adaptation, a soft-bodied king ruling a kingdom of crushing pressure and eternal night. The ocean holds its secrets tight, and the colossal squid is the greatest secret of them all, a ghost in the machine of the Antarctic that we are only just beginning to understand. As we ascend from the depths, let the cold fade and the warmth of the surface return. The water is calm, the ice is far behind, and the rhythm of the waves rocks you gently into a peaceful slumber. The monsters are far below, swimming their slow, silent loops in the dark, safe from our eyes and our world. If you enjoyed this dive into the Midnight Zone with the largest invertebrate on Earth, I invite you to leave a like, subscribe to the channel, and share your thoughts in the comments below. It helps this little submersible of curiosity find its way to other sleepy travelers. But for now, let the current carry you. Let the water hold you. You are safe. You are drifting. Good night.